All right, well, welcome everybody to the ME 520 Mechanical Engineering Department seminar. Today we have Ashis Banerjee, who's a faculty in Mechanical Engineering and Industrial Systems and Engineering. Again, as a reminder, please mute yourselves for the talk, but then we will have a Q&A at the end of his presentation that you can either unmute yourself or raise your hand or try to get our attention for your questions. Before we start, I'd like to give an introduction to Professor Banerjee to everyone. Ashish got his undergraduate degree from IIT Kharagpur in 2004. He then came to a great university, University of Maryland, where he was a terrapin like myself. Did you go to any basketball games while you were there, Ashish?
Yeah.
Oh, good. Of course, you have to. But he was there for his PhD and master's degree working with S.K. Gupta until 2009. He then went up the East Coast to MIT as a postdoc in the CSAIL lab. He was there for a number of years before actually taking a position as a research scientist at GE from 2012 to 2015. And then he joined us here in mechanical engineering and industrial and systems engineering in 2015 and has quickly built up his lab. His work is in digital manufacturing, predictive modeling, autonomous robotics, his funding in these projects has had both a kind of a standard funding, but also very interesting industrial partnerships. So his work has been funded through the Department of Defense, but also projects with PACCAR, with Boeing, Amazon, and Novo Nordisk. So this is a really kind of taking stuff that we do at the university and really trying to implement it towards actual change in industry. So I think Ashish is one of the people that really excels at that kind of work. So his talk today is going to talk a little bit about what he's been doing, but without further ado, I'll let Ashish go ahead and take it away.
Thank you, Nate. That was a very detailed introduction. So today I'm going to talk about a collection of research projects that we have been doing in my lab, primarily focusing on some form of robot learning. And before that, I'll give like kind of an overview of all the stuff that we do in my lab, because there are lots of students with very diverse backgrounds, and the projects also like span many different disciplines and application areas, and sometimes people wonder like, what do I exactly do? So here is kind of an unifying theme among all of these different projects, where we sort of focus on the central objective of developing these automated decision-making methods for a variety of real-time systems. And by real-time systems, that can include many things. Those are all engineering systems, but they can be in the manufacturing space, they can be in transportation, like we are talking about self-driving cars, for instance. They can be in warehouses to help or facilitate workers, which kind of has now become an even more important topic in the wake of COVID-19. So all kinds of different engineering systems, and also in one of our new projects that will be starting off with Novo Nordisk, that will be on the healthcare sector, but that's not what I'm going to talk about today. And the overarching goal here is that can we achieve system level performance that surpasses anything that has been seen today. And by that, I mean like we just don't want to enhance the efficiency of one particular machine by 5% or utilization of something by 7%. So that's not our goal. Can we like bring about these really meaningful improvements or enhancements to system level metrics, such as the overall productivity and throughput, but also focusing more and more on safety related issues from the workers' perspectives, as well as like if it's more of an individualized system, like someone driving a car and it's kind of autonomous or semi-autonomous, can we do something to enhance the safety of the people riding that car? So we are talking about those system level performance metrics, and whether these decision-making methods, when implemented in real time, can really make a huge difference in those metrics. So in order to do that, kind of the projects in my group are like fall into two broad categories: one which basically use robots in some sense, or the other, and the other category where we do not use robots. So in all the cases, we rely quite a bit on machine learning. We do a lot of statistical modeling, but it may be purely from the perspective of predicting outcomes given some rich data sets, or we may want to take that a step further and actually make use of those predictions and put them on real robots to see how they can be of assistance. We also work on human aspects quite a bit, and that brings me to the topic or the type of systems that we are going to talk about today, which are cyber-physical systems. So traditionally, engineering systems kind of operated in these sort of silos. So you would have these machines which may be manually operated or automatically operated. That's fine. They can be CNC machines. That's all of those fine. But then like you would separate them out from like real interactions with humans, as well as sort of treat the computer control and command of those machines as the separate entity. Now what's happening is that these traditional engineering systems are getting morphed into what we call cyber-physical systems, where these interaction among these computational, physical, and human entities are the key driving force. And why do we want to have this kind of interaction? For enhanced flexibility, enhanced agility, as well as resiliency. So if we just treat each entity in isolation, then if one group somehow runs into some issue, say like you now have COVID-19 and bunch of your workers cannot like actually show up to run these operations. So if you think everything in isolation, then the whole system would break down and you will not be getting any benefits out of it. Whereas if you look at it more from a perspective of interactions that can be synergistic, then you will build much more of these adaptive and resilient systems which can respond better to emergency situations. It can even respond better to disturbances that you would expect even under normal day circumstances. So this interaction and integration or coupling plays a key role in modifying the behaviors that we see emerging out of the cyber-physical systems. And while those behaviors have these benefits of making the systems more agile and robust and all of that, they also now pose some other interesting challenges which we as researchers love to get engaged in and try and address them as best we can. So some of those challenges include now we are talking about these inherent coupling of operations happening at different spatial and temporal scales. So if like you think from an enterprise perspective, you say it's a manufacturing enterprise. So one way to think about it is you have this huge company where you have the bottom lines for the company, and that's what is sort of what the public perception of the company is and drives its market value and all of that. But then you like go down the hierarchy and you come to these individual processing units at one of maybe 100 different factories that might be responsible for running all the operations of the company. And you look at that level, the scale of operations is very different. But now what used to happen was that people in that workstation would be only responsible for the job there, and no one else would really care about it. They will be handed down some requirements that you need to run it at this level of utilization efficiency, and as long as you meet that, everyone is happy. now with this integrated coupled framework, whatever is happening at those workstations at an individual level is still going to impact what happens with the company or the enterprise as a whole. So with this now gets this additional challenge of how can we sort of orchestrate all of these resources, each working at its own kind of time scale and impacting these operations at varying spatial locations and with spatial distributions. Also, like sensing and perception now has become very important. So you may have heard about all the smart factories and so on in smart cars. So a large reason why they are called smart is due to the fact that we have all these instrumented sensors that are pulling in information at such a rapid clip. And then the challenge then becomes we have to make sense or be able to process all these sensory feed in real time. And by real time, it's typically several hertz. So that's non-trivial just to do it for one car that's on the road. And now you imagine if you have to do it at, say, a factory level operation, it becomes quite a challenge. And also then the behavioral modalities become quite diverse. So for instance, like for a self-driving car, which is a smart cyber physical system, it is expected to behave quite differently if it's in this urban congested roads versus it's driving on a freeway in like very nice weather with no rain and all. So it can't be exhibiting the same kind of behavior under all situations. One case, it may have to drive much more conservatively or so as to ensure pedestrian safety and all that. Another instance, it might be expected to actually drive quite aggressively. Otherwise, like the human drivers would really get not very happy and get mad at what is this slow moving, whatever self-driving car that's out there on the road. I don't want that. So why doesn't it move to the right lane and let me go on my own way? So it's expected these systems that they would inherently have the capability to exhibit different behavioral modalities. So all of these are new emerging challenges. And kind of central to many of these challenges is we have so much of these resources that are available to us. How do we make the best, or in some sense optimal, as well as robust utilization of these resources, so that ultimately we have some meaningful enhancements to system level objectives like productivity and safety. So it can be done in many ways, and like hundreds and thousands of researchers are looking at it from different perspectives. So one approach that we have adopted in the lab is to see how and where autonomous robotics can make a big impact in addressing this core challenge of making use or best use of the available CPS resources. So specifically, we want to look at questions like whether the robots can help in deciding which computational components are beneficial under what context, how can they control and command some of the physical entities, and also very importantly, how that's going to shape human interactions with those systems. So in order to solve these sort of like very practical problems, the core technological paradigm that we have adopted is machine learning, particularly now with the advent of a lot of high performance compute resources and corresponding machine learning models that leverage those compute resources, and all these data that's coming in through the sensors. We naturally have a rich collection of data. We don't have to worry about running experiments to get data in many of these systems. Can we make use of these advances in machine learning, put those on autonomous robots and help them make most good use of the CPS resources to drive the system level metrics? So that's kind of the theme or focus of the research. So to drive home some of the work that we have done, I'm now going to talk about 3 different applications, and we'll see to what details I can get into each of those. but I'll quickly begin with the first case study of using visual perception, which is basically an RGBD camera fitted on a robot to help with assessing the ergonomic risks of workers as they are manipulating objects in indoor settings, especially warehouses. So technically speaking, the challenge here is that we get all these video frames in some kind of sequence, and the task here is to be able to make sense of those video frames to identify when, like, a human is performing what kind of action, and these actions again are restricted to object manipulation actions. And once that action can be recognized, also link it to some corresponding ergonomic risk measure. Now, why do we care about ergonomic risk measures? That actually has a lot of implication from the societal and economic and healthcare perspectives. So you may or may not be aware of this fact, and this is somewhat of an outdated number. The number has actually risen, that even in 2016, there have been close to 350,000 reported cases of musculoskeletal disorders, which can all be correlated to carrying out certain actions in an ergonomically unsafe manner and over a period of time repetitively. So that, of course, has huge implications. Not only the amounts to tens of billions of dollars in healthcare costs, but it also means that you are losing out on this skilled workers for several weeks to up to months if they do have MSDs and they need to recuperate from them. Also, sometimes the workers, after having such MSDs, they would just leave their current jobs and either retire or do something else, and that is a big blow to the companies that were employing them, because it's not easy to replace that kind of skilled labor easily. So the idea here is that human-robot collaboration can help, where a robot can either be a passive monitor of like what kinds of actions are more risky and which ones are acceptable, and then accordingly it can provide some recommendations on how to mitigate the risks if possible. And in other cases, which we have not done yet, but it's super useful if we can get there, if as the robot acts as an assistant and actively helps out the humans in carrying out those higher risk actions. So in order to do that, we have to start off with some kind of an ergonomics risk assessment model based on the biomechanics of the human postures. And there are many ways to do that. Some of the models are very involved, but we decided to use one which is approved by NIOSH, at least for industrial applications. And it's actually quite popular in the construction sector. It has never been very widely used for some reason in manufacturing and warehouse industry, but now with more of these MSD cases and the demand for skilled labor, ergonomists in these sectors are also looking at such models. So this model is called Rapid Entire Body Assessment, or Reba in short, which the output is extremely easy to analyze. All that it gives you is a score between 0 to 15. And from this table, you can see that depending on where your score fits, you will be assigned a particular risk level. Now, if you fall in this medium or high risk category levels, then it's not that immediately you run a risk of injuring yourself or suffering from back pain, shoulder pain, none of those. But gradually they build up over time, and typically in like a 15 to 20 year time period, you will see the effects in the form of these MSDs. So what Reba does is that it basically looks at the sort of key joints in the human body. It divides those into two groups based on whether it's the limb motion or whether it's the neck and the trunk and other parts of the body. And basically it tries to estimate how much of like an impact, the load or the force that you're exerting in carrying out this particular activity is being imparted to those joints, and tries to estimate the effects of those loads and forces in terms of the joint angles and the torques. And if the angles are above certain thresholds, or if those exerted torques are beyond certain values, then it's going to assign a high risk value for that particular set of joints impacted by this action. So here we did like the simpler thing, since we are just relying everything based on camera videos that we cannot directly estimate torques and all. So we just relied on building a skeletal representation of the humans in real time and using those joint angles as the surrogate measures to figure out what the individual risk scores would be. Also, like if you keep on doing the same kind of action repetitively and it's decently high risk action, then that has a compounding effect on the score. It's something that is should be avoided. So that like gives you a higher score than normal. So we get some kind of like numeric score on the risk level of the activity based on this Reba model. And then what we do is we'd rely on this particular machine learning pipeline to train our robot on how to categorize these actions. So what we have during this training phase, which we can see in this like upper section of this particular flowchart, is that like there will be this collection of videos, and I'll talk in a minute about what kind of data that we generated to get the right set of videos. So say we have this stream of videos, then we have to do this step of annotation, which is somewhat of an expensive step. It is not fully automated, so it does require some manual intervention, and it's partially automated. So in the annotation step, what we do is that we basically segment up the videos or divide up the videos into these chunks of frames, where each frame corresponds to one specific object manipulation action. And all these different frames corresponding to these different actions, they are fed as those training images to a very popular deep learning based image processing module called VGG16, which has the 16 layers of convolutional networks and the usual pooling layers and so on, which then tries to like extract some useful features that will correspond to the specific actions that it knows exist in those given frames. And when we deal with video as frames, basically each frame becomes its own image, and we can treat each image separately. Now, the other thing here is that the temporal aspect to it. So it's not pure image processing, because here we are dealing with videos and actions that have certain durations. So each action may last for a few seconds or tens of seconds, and then the person is going to transition to another action. So it's not just pure static images of different objects that we are trying to process here. So the temporal part is also important. So the first half of it can sort of deal with all the spatial features, but to capture more of the temporal nature of the actions that are being performed, we feed those learned features from the VGG16 model, and again give it as inputs these video frames, but now in the correct sequence. So the sequence here is very important in the bottom section, which is hopefully going to help the model to learn that if some frames occur in a particular order, that means it's certain kind of action. And then like if it's in a different order, then it's a different action. Or it would also hopefully help the model to learn when one action ends and the new action starts. So in order to do that, we had to use another different deep learning network, which is more geared towards picking up these temporal patterns, and it's called temporal convolutional network. So once we combine these together in this sort of pipeline, then we have a final model which is able to like identify which frames correspond to what actions, and when do those actions end and the new action would begin. Now you see here the Reba scores also appearing here. So by virtue of being able to segment the videos into these actions, it now also knows that the risk levels of those actions. So if it's say an action of picking up an object, it may have a risk score of say 5 or 6 on the Reba scale. So once it can identify this is picking up an object type action, it will immediately also know what the corresponding Reba score is. And that is what we can then use in more of a real-time operation mode for the robot to inform the workers about not just what action they are doing, but more importantly, how risky the action is. So that kind of comes for free by virtue of building this whole pipeline. So I won't get into too much of the details of the architecture itself of VGG16, the interest of time, but there are lots of details here for all these models that I'm going to talk about today. So anyone who is interested, we can discuss more offline. But one key point here is that we took the standard VGG architecture and then we did some modifications which helped with performance. We also fine-tuned some of the last few layers of the VGG16 model for our specific data set, which, as we will see, also had a little bit of an improvement in performance. The actual or the original VGG16 model has been trained purely in terms of learning the model weights and hyperparameters using different data sets, not ours. So fine-tuning it on our data set normally helps with these models. And then we have the temporal convolutional networks, which have a very different architecture with these hierarchy of what we call temporal convolutions rather than the normal spatial convolutions that we see in the regular deep learning networks. And it's not that deep in terms of the number of layers, but each layer is kind of long, which helps in capturing these sequence of operations. And we have two variants of those, which again, I'm not going to get into the details of how they are different and all, but they are quite different from the regular deep learning models based on convolution layers. So that's kind of a message from this slide. So then coming to how did we train and test it, and to what extent were we successful? So first, we tested it on this open source data set that was created at Technical University of Munich, TAM, and it's on for a kitchen where, as you can see, this person is doing regular household activities in a kitchen, and that's why it's called the TAM kitchen data set. So we have like 19 such videos, and each video is fairly long by at least video processing standards. It's 2 minutes worth of activity that is happening, and within these 2 minutes, the person may do a bunch of different actions like just walking and standing to reaching for cups and plates, or placing cups and plates in different racks and shelves and so on. So we divided that up as usual into training and validation samples, all the individual frames from the 19 videos. And one thing that is worth pointing out is that it does have a large number of action classes. So it's not a very simple classification problem in the sense that you just need to identify either the person is doing action A or B or C. There are lots of actions the person can potentially do, and it's non-trivial for the computer to be able to learn which one is being done when. Okay, so that was for a kitchen setting, but really our target application is for more of warehouse style applications or factory applications where workers would be manipulating objects of different kinds, and as a result they would be bending and twisting the body. And we know from ergonomics principles that it's those bending and twisting and stretching motions which typically correspond to these greater risks of having MSDs in the long term. So that was also reflected when we managed to run Reba on our collected videos. But first we had to generate those videos, which means we had to recruit volunteers, we sort of set up a study in a lab controlled environment where we asked all the volunteers to perform a fixed set of object manipulation actions where essentially the objects had different shapes and sizes, and you had to pick up and place them at different elevations from the ground level. So for this data set, we ended up having 17 action classes, which is still a very high number. And we see some representative examples here in these snapshots where, as you can see, as someone, the PhD student working on leading this project, as she's bending or moving her body around, those correspond to higher or at least medium level risks on the Reba scale. So with all of those data sets, then it was time for us to see how well our model would work. And in case of video processing, this kind of diagram is typically useful in understanding how well these actions are being recognized. So what we see here, so it's worth spending some time understanding what all these colorful stuff is actually telling us. And then we can look at the numbers. So we have 4 different models here. 2 of them are these spatio-temporal convolutional networks, the kind you saw in the pipeline image that I showed earlier. And then you have like a traditionally used active action recognition model, which is very popular, but as we will show here, it's not particularly useful for our application. And then SPM is a very traditional machine learning classifier, which is not expected to perform well under these settings because it does not capture temporal patterns in any specific way. So what we are showing here is that for each of the models at the top, we have the ground truth values, which basically are those annotated video frames. So if you look at any of these block of frames, you will see that they will correspond to one particular action. And of course, you will have these contiguous blocks. You cannot suddenly start an action and then half a second later transition to something else. You have to like carry on this action for at least a few seconds and then move on to the next. So that's how we have these contiguous blocks of actions, frames corresponding to actions. And then we, at the bottom, we have the predicted outputs. Can we predict at an individual frame level what action it is, whether that matches with the true action that has been performed? And also very importantly, can we model these transitions from one type of action to the next type of action properly? So the durations of the actions and their transitions both are important. And clearly, visually, you can see that we kind of progressively do worse as we move from like our preferred model to one that has been shown to be useful in other domains, plus the standard classifier, which is not very suitable at all. And those are reflected in these tabulated numbers as well. So the accuracy values may not seem that impressive, but for video analysis, accuracy is really not something people care about that much. Instead, what is more important is to look at these 2 metrics. For example, the overlap percentage, which is kind of intuitive to understand. So what we have here is that there is no real ground truth. So it's all based on annotation. So someone may annotate like this particular action A has ended at 12.7 seconds, whereas the same video someone else may annotate and say, oh no, I think that ended at 12.8 seconds. So there will be this sort of subjective bias in annotating the videos. And the subjective bias is kind of compensated for when we look at this overlap measure, where it's more important that you have the right transitions of the actions and roughly their same durations, rather than trying to match everything frame by frame basis. And we do see that our method works well when we consider these more robust measures of performance. So this is for without fine-tuning the VGG16 model on the kitchen data set. We get little bit improvements when we do fine-tuning. And then when we move to our data set, we see an even more stark difference in performance. This particular model by far does better than the rest. And in fact, the common choices of models that people might think of, they do really poorly, as you can look at these numbers. The same thing with even better performance. So we reach more than 93% in terms of overlap measure when we fine tune the model for our specific indoor object manipulation data set. And by the way, this data set is available to everyone free of cost for you to download and make use of if you want to. It's quite a rich data set if you want to ever study something on how people or how human postures vary as they are moving objects in indoor settings. So I would encourage you to use the data set if at all it makes sense. So that's about the first case study, and we then put it on a collaborative robot platform in the passive mode, and it worked reasonably well in real time. We did encounter some issues with like the scene itself. So the scene in which we trained our model and the scene in which the robot is actually operating are quite different. And as I will talk at the end, these learning models tend to be quite brittle to these workspace space conditions, and we are trying to address that in our current research. But in any case, so that diminished the performance a bit, and there were some other challenges, but overall it still was quite successful in being able to monitor in real time which activity is happening and then assigning a corresponding risk label to that activity. So we have published that work, and I would again encourage you to read our paper or talk to me if you have more questions about it. Okay, any questions so far before I move on to the next topic?
I'm on Zoom right now. Can you call me?
Sorry?
Sorry, that was just a background. Go ahead, Ashish.
Okay. Okay, so let's move on to the next domain that I wanted to cover, which is on related to self-driving cars, and maybe not fully self-driving, but definitely quite high in the level of automation. So we have these 5 levels of automation for these cars, and right now most of the cars that we drive in are probably level 1, maybe level 2, but here we are talking more of 3 and 4, if not 5. So one thing is that people have been working on these self-driving cars for at least a decade now, and I have many friends who are leading many of these efforts in several places, both in direct academic research and in the industry research, and they would all tell me, like on a more or less with consensus, that like the technology is largely there, barring 1 or 2 really thorny issues which are kind of hard to address, like for instance, how do you drive in like very bad weather conditions and so on. But a lot of the technology is already there, but it has been a very big challenge still to like get it into the public space. And forget about like actual cars, it's even not that that we see a lot of these autonomous delivery vehicles, whether it's from Amazon or Uber or anything else that is like doing the job. In fact, there was an article I was reading that in COVID-19, this should have been the ideal time for those delivery platforms to have a real world impact, but it has been very limited, to say the least. So there are lots of these socio-technical challenges that need to be addressed before they become more of a commonplace occurrence in our day-to-day lives. And I'm going to focus on one particular aspect of that challenge, which is a common complaint that people would have as they try out these highly automated cars and see if that's something they are willing to invest in. The fact is that every one of us have our own kind of driving style, and maybe we have many different driving styles, but even if you consider a broad categorization of whether we drive in a very conservative manner or in a much more aggressive fashion, that is something we want to be reflected in also in the vehicles that we are owning or the vehicles that we are going to be using. And that's not there. So right now, these self-driving cars or highly automated cars, they have this one kind of common theme of level of automation, and that's what they're going to stick to. And based on what kind of hard coding has been done, they are going to deal with these different driving conditions in pretty much identical manner, no matter who is the owner or who is the user and what their preferences might be. That is one of the many reasons why these cars are finding a hard time to gain acceptance among potential users. So what we have recently started doing, and this is like really fresh work, it's yet to be published. It's something that one of my PhD students just recently finished getting some results from, but the results looked kind of interesting. So I thought I'll be sharing those with you, and it's a very different domain from warehouse and manufacturing. So it kind of brings some flavor diversity to the talk. So what we have been trying to do is, can we make these vehicles more personalized or more adaptive to the differences in the driving styles or behaviors of their users or owners? Now, in the literature, people have done some studies on this broad classification of drivers, and the one that is most popularly accepted is this 3-level categorization of drivers into conservative, neutral, and aggressive, and the names are like mean pretty much what they say they are. So what also has been shown in those studies is that like sometimes due to the way they are hard-coded in terms of automation, they in fact show exactly the opposite kind of behaviors you would want your own vehicles to show. They are far too conservative for if you're a more aggressive driver, and vice versa if you're conservative. So first research question then is, lots based on all these data that have been gathered in these studies, and almost all the big auto manufacturers and all the big tech companies have conducted their own studies. So there is no dearth of data if you want to analyze that. So based on all of that data, can we like learn these driving styles, which is in a way meaningful and interpretable to a computer, or can be then fed to some other like machine learning module to then like come up with like actual behaviors or policies that the cars could execute? So that's the first question, and although it may not seem like a very big challenge, it's in reality quite a challenge, because the data, although there is lots and lots of data, it's quite messy, and the bigger problem is that the data is not labeled. So if we have labeled data, then machine learning usually has a field day. But if it's working with unlabeled data with some quality issues and some things that have not been recorded properly and all, it's a much harder problem. So how do we annotate or label the data? How do we deal with some of these quality issues? And also at the end, however we make use of the data to make the cars learn some useful policies, how do we interpret or explain those policies in a way that makes sense to us as humans? Because sometimes many people would use these learning models as sort of black box, and they will just give you some outputs and not really be able to tell you why these variables are having this kind of an impact, or what do those outcomes even really mean in real world scenarios. So these are some of the questions that need to be answered. So in order to do so, we relied on a data that was primarily collected by Toyota in and around the University of Michigan. So it was with the partnership of University of Michigan, I believe, Transportation Research Institute. So you can see here Ann Arbor campus, and basically they had a bunch of like drivers, a fixed set of drivers drive around these US highways surrounding Ann Arbor. So all of them basically would start from this point here, take this route 23 and then this combine 14 and 23, and then basically end somewhere around here. And then they would do the trip in the other clockwise direction. So both clockwise and counterclockwise. So what we first started off doing here is that we have these raw measurements of the speed and acceleration and that we have from these cars and the drivers who drove those cars. So this is not for any self-driving car study. These are actual human drivers who rode those cars. And we had like a little more than like 100 such trips for this particular set of highways. So the first thing is, can we kind of fit a function to this data, which would then make it easier for us to use that function to come up with this classification of driving styles. And for that, we relied, we did function or car fitting, but we did not just do like very default linear or polynomial car fitting. Instead, we used something called B-spline basis functions, which has some nice properties that if you can choose these not vectors or not points appropriately, you kind of can adjust the level or accuracy with which you can fit your functions, no matter how complex your raw data might look like. And it did turn out that here that if we choose the not vectors fairly closely spaced out at 100 meters interval, and we choose an order 4 B-spline basis functions with 67 such piecewise basis functions, we can capture the speed profile of the drivers. And we could have done it for other things like acceleration and so on, but it turned out that my modeling speed, we got the best sort of class categorization of drivers into different groups. So one thing interesting here is that when drivers are sort of transitioning from this one interstate to the next one, that means they have to take some exit and all, they invariably have to slow down to take the ramp and so on. So that always gets reflected in the speed profiles, whereas that's something which is not always clear if we are looking at other things like acceleration, for instance, or some kind of lateral displacements of the car also from lanes and so on. So once we fitted these B-spline functions, then what we did is we ran PCA on it to sort of identify like which of those are the key ones. And since in this case PCA is run on a functional space rather than our regular input space, it's called functional PCA. And we indeed found that 6 of those functional principal components can pretty much explain most of the speed variations that we have. And interestingly enough, you will see, like if we just zoom in on these highlighted junction regions, the different functional principal components actually capture the effect in very different ways. In some cases, they reflect that very accurately. In other cases, they may capture more of the changes in speed between aggressive, conservative, and neutral drivers as they are approaching the ramps. In other cases, you may see that they will capture the behavior of the drivers better as they exit the ramps and move on to the next highway. But these 6 are, if we just take them into account, that's usually sufficient. And using those, we then ran the very basic k-means clustering, and we could come up with this clear differentiation in the speed profiles depending on the driving styles of the humans. So then what we did was that we found out that about, I don't remember the exact breakdown, but say 20 odd were in like one category, 30 odd in other category, and 50 other drivers in the third category. So then we could segregate our entire data set into these 3 categories of drivers and train our learning models individually on each of those different driver categories, so that finally if we have to make a vehicle exhibit the same kind of driving style as their users, the expected behaviors would match more closely with what their users typically do if they are driving manually. So that's the intent behind all of this clustering and data analysis. So once we had that, this time we decided to use a reinforcement learning framework, and more specifically a deep reinforcement learning framework, where here the agent is basically this autonomous car, and it is going to try out different actions that depending on the state. And by state, as I will show soon, it means like what is the speed of the vehicle, how far ahead on its lane is the next vehicle, how far, whether you have another vehicle on the immediate left lane, whether you have another vehicle or set of vehicles on the right lane, because those would all govern like the actions this car would take in terms of either being on the current lane or switching to different lanes. So in the training phase, it's basically going to try out this bunch of different actions, and then it's going to get some reward from the environment. So in our case, the environment is actually all the information that we already have about typical human driving styles or behaviors. So that comprises our environment, and we have a way of automatically learning what is a suitable reward function. So that reward function, then whether it's a positive reward or negative reward or high positive reward or high negative reward, all of that is basically going to tell the car whether this particular action or maybe moving to the left lane is something which is preferable, or it's something that should not be done based on the current state. And then it's going to do a reprocessing of the state variables using this deep neural network, which is really not that deep in our case. It's just 2 hidden layers with 30 units in each layer to come up with a new policy or an updated policy, where policy is nothing but just a mapping from state to action space. If you're in this state, you take this particular action. And hopefully the updated policy is a better fit for what the agent should have been doing, but it's going to test that out again by getting a new set of rewards, and after a point, we hope everything would converge. Now, one thing that is very challenging in these kinds of frameworks is how to fit in a reward function. And you can try and do it manually, like give it some kind of own function with some parameters that you magically conjured up. But the better way to do it is also to learn that reward function automatically based on these driving profiles for the 3 different driving styles that we identified. And that is the inverse reinforcement learning framework. And we adopt again a specific variant of it, which internally approximates the reward using another like convolutional neural network. But it's the same overall idea. So if we do all of that and we have these 4 state variables that we considered, each variable discretized into 4 or 5 different levels, then what we see is that the first thing to ask is whether we are able to learn a useful reward function, and then based on that reward function, whether the policies that your car is learning, whether they make sense, whether they sort of match our expectations of aggressive driving versus neutral versus conservative driving. And we indeed see that that's being true for the most part, although we still have many challenges with the data. For some instances, we have no information about the left car present or not present. Same is true for the right lane. So those mess up the calculations a little bit, but still overall, the results make sense. That we see that in general, aggressive drivers are itching to take some actions. They are never very happy sticking to the current action, no matter what state they are in. So that's why you see lots of these higher negative numbers in these reward function heat maps, so to speak, for the aggressive drivers. For the neutral drivers, it's more of a mixture of positive rewards, negative rewards, and then for the conservative drivers, they would tend to stick to their current action. And so you see like the higher positive numbers showing up in most of these cells. And the same thing we can see if we look at like a detailed sort of policy computation probability table, that, for instance, here we look at the scenario where the car is the main car, which is the autonomous car of interest to us. It's driving at a fairly low speed, and there is a huge distance in front of the car. And what we are trying to see is that whether it's able to come up with meaningful behaviors of when to change the lane versus staying in the current lane, depending on what the variable values are for the left lane and the right lane. And we see, if we go over and parse these rows carefully, we'll see for a majority of them, the actions make sense, or higher probabilities mean that action is more likely, and that those are the cells that we have shaded in blue. On the other hand, if we move to neutral drivers, we instantaneously see that a lot more of these shaded cells now belong to the stay in current lane, and only in few cases where it's quite confident about taking a different action does it decide to change to left or right lane. And if we move to conservative drivers, it's quite interesting, like how conservative drivers can really be that is, unless you really have to take a ramp for an exit and all, no matter what the distances might be, they would always tend to stay in their current lane. Okay, so that's all about self-driving cars. I don't have much time, like a couple of minutes, so I'm not going to get into all the technical details of what we are doing for the third case, which is a very different kind of robots, but I'll just quickly explain what the problem is and how we are trying to address it. So in this case, we are not talking about cars, we are not talking about collaborative robots in factories and warehouses. Instead, we are talking about robots that we cannot even see with our naked eye, but have to be viewed inside a microscope. And this is in fact the whole setup for it. And each of those tiny robots, which are basically microscopic particles or can be biological cells, they can be actuated using this focused laser light in the infrared regime. And then you can treat them each as a micro robot, which can move around in this workspace and form some interesting patterns and which we can then study. Or you can also think of those as being manipulated to form some assemblies of shapes and structures. So very different set of spatio-temporal skills we are talking about, but kind of the same set of challenges in terms of being able to learn what should be suitable behaviors of these micro robots in these high dimensional uncertain state action spaces. And couple of things that we have done is, one is on the image processing side of it. So as you can see in these images, the images are pretty hard to parse even with human eyes. We have like this dense collection of these objects, beads and particles and cells, and they are often tightly aggregated together and all of that. And it's not easy if you use standard image processing methods to be able to segment out and really identify which object lies where. So we used the semantic segmentation method, which uses a particular kind of deep learning framework, and we jump into the results, we see that it works really well. Like we were pleasantly surprised at how well it's able to detect the boundaries of these objects. So that's kind of the first step. Now we can detect the objects, but can we now make use of that information to control the motions or plan for the motions of these objects in these uncertain environments? And for that, we use a different learning model, which is based on some recent work on using model predictive framework, but using in a smart way with importance sampling. We don't yet have the full physical experiments for that done in 3D yet, but at least in simulation we have shown, and we have done some 2D experiments in a plane. We have shown that that works out pretty well in terms of avoiding obstacles and going to their desired locations to form the patterns that we want them to do. Okay, and we have some results indicating like how scalable this method is and where can you expect a drop off and you can no longer get real-time control. So those are like some successful applications, all within the theme that we have these very different cyber physical systems at different spatial and temporal scales, requiring different kinds of behaviors depending on the context or scenarios. And can we make use of robots which can learn from data and make use of those resources judiciously, so that we either make the experience better for human users or safer for humans, or like achieve some high productivity and throughput, as in the case of the micro robots example. So the work is by no means done. There's lots of scope for future research directions, including how to make these models more robust or generalizable, how to be able to extend those for interactions with arbitrary set of objects, or also to be able to forecast what would be the next set of actions that humans are likely to perform, so that the robot can actually tell the human in advance that you should not be really doing that activity next, because it's only going to mess up your ergonomic scores and you'll really be in the risky category. So those are problems we are looking at. Similarly, like for the driving domain problem, it's by no means solved if we want to scale it up for all the possible state variables and the kinds of actions that a car might want to take. We just looked at a very restrictive set of actions of lane changing versus not, but there are so many other things a car needs to do in self-driving mode. And also, very importantly, how can we enhance trust of humans in these in these cars by sort of aligning their behaviors more closely with human behaviors. And then, as I said, like we don't yet have the full experiments done for the micro robot case in case of 3D manipulation. So that's also something we are working on actively. We have some of the challenges already taken care of, but a few remain. So with that, I would like to acknowledge all the students and collaborators, and also like the various sponsors. So as Nate pointed out, many different sponsors here, and also NSF supporting one of the students for the research directly. And some collaborators here. And with that, I'm open to any questions, and thank you for spending an hour with me here.
Thank you very much. I'm gonna unmute everybody so that way we can all applaud together. Ready? 3, 2, 1. All right. So we have time for questions from our audience if people are available to ask. You can either go ahead and, I'm gonna mute everybody real quick. You can go ahead and unmute yourself if you've got a question. I'll start off, Ashish. What kind of driver are you? Are you moderate, conservative, or aggressive? Neutral, sorry. Oh, sorry, you're muted. I apologize. I can unmute you. There you go.
Yeah, I think I will be in the neutral category, and that's what like studies have shown, like but roughly like 50% of the drivers would be in the neutral category, or maybe 45% or so. Yeah, so, and typically the ways people design these automation modules in the cars would be geared towards this neutral category of drivers. And that's why many studies have shown that if you are more on the conservative side or aggressive style, you are very likely to be pissed off at the way these cars are driving. So those are more of the like target segments where like the cars, if they adapt their behaviors, they are likely to gain more trust and acceptance.
Thank you. Yeah, I do think it would have been a great opportunity to test drive auto driving cars a month or so ago when the roads were clean and quiet. I think now there's too much traffic for that. Any other questions from everybody else? Go ahead and unmute yourself if you got a question.
I had a question about the ergonomic risk research. I found that really interesting. I was wondering, how do you validate the Reba model?
Yeah, so that's a great question, and there is no simple answer to it, but I think the best answer I can give it is that when we did all these evaluation of how well the learning module did, we worried less about whether the Reba scores themselves were highly accurate or not. We were just trying to see if we can predict the correct Reba scores, even though the correct might not be really the correct ones. Now, increasingly, what we have done over the past 6 months or so, which I have not covered in this talk, otherwise it would have been all about that project only, is basically start a lot of these pilot trials where we have a smartphone version of our like app, which does this real-time monitoring, and we have started doing these pilot trials with an organization called Washington Retail Association, which is actually an organization that is kind of managed by the Washington State Department of Labor and Industries as a sort of intermediary link to many small and medium scale enterprises which are insured or which do worker insurance through the state. So they don't have their private insurance like Amazon, they get state insurance. So WRA, or Washington Retail Association, is kind of an umbrella organization that helps them sort of get help in terms of worker health insurance and occupational safety guidelines and so on. So they are in the process of running these pilot trials, although we have been delayed quite a bit over the past 2 months, obviously, where like they have their own specific like test cases where they kind of can validate the scores that we report or which we learn or predict, whatever, with like some comparisons based on years of like manual observations and recording of those actions that like people have done in those companies. So the challenge is that in those companies, there would be 1 or 2 ergonomists, and they would run those assessments maybe on a quarterly basis or on a semi-annual basis. And then like for the rest of the duration, the workers really don't have any way of assessing how risky their actions are and how maybe that can be mitigated and so on. So we are trying to do some validation based by comparing with those paper trails or paper-based assessments run by expert ergonomists to gain some more credibility that these are indeed realistic measures. But then our sort of selling point here is that if you think they are reasonably good and valid, then you can really run them continuously in real time and not having to do just one assessment every 3-4 months.
Excellent. Thank you.
James Mills had a question. James, do you want to unmute yourself to ask your question?
Yeah, my question was, what is the time response of the system to eliminate accidents or failures?
I did not quite follow your question.
Okay, what is the time response of the system to eliminate accidents or failures?
Which system?
The system that processes all the data?
For the ergonomics one?
Yes. Or
yes. Yeah, so the processing time is of the order of 100 milliseconds or so, but there is one other challenge that I kind of glossed over, that like it does need to get a few frames of a particular action before it is quite confident that it knows what action the human is performing. So typically we would have that kind of tuned lag of 3 seconds where we would let like someone performs an action for 3 seconds or so before like letting the computer on the robot tell that, okay, this is the action and this is the estimated risk score for the action. Even though in reality it only takes hundreds of milliseconds to know which action it is, but it does require few frames of real observations in actual operation mode before it is confident about its prediction.
So on Reddit, there's a lot of these videos about like basketball hoops that will adjust themselves to be able to help you either make your shot or block your shot. Are those also needing to be sort of conditioned with some 3-second adaptation to a user to be able to then.
So some of those actually have less adaptation time periods simply due to the fact that they have fewer list of actions and very well-defined actions that they need to care about. So either a person is like dropping a ball and, but here we have a more richer set of actions as people are manipulating objects. You can manipulate objects of different shapes and sizes. You can pick and place them from different heights, and accordingly you will be like twisting and stretching in many different ways. So even the 17 that we came up with was a pretty coarse, at coarse granularity. We could have done even better in terms of the granularity of action. So it's a somewhat simpler problem which many of these sporting goods have implemented. So I don't think they need 3 seconds. If I were to guess, although I have not played with any of them myself, it would be more like 1 second for them.
Thank you.
Thank you.
Other questions from our audience? If you'd like, you can enter into the chat for a question if you want me to call on you. Going once, going twice. All right. Thank you, Ashish, very much. I think that was a great talk.
The opportunity. Yeah, there were lots of people who attended, so at least there were some people who were interested in the topic. Hopefully they got some useful information as well.
Thank you again.
Okay, bye.
Bye, everyone.